Hello and welcome to the next video in a series which is aimed to help you with your mathematics for computing module and explain a little bit more about the mathematical content and show you different examples. In this video we are going to talk about relations, and for that first we're going to review what a Cartesian product is, then look at the definition for relation, then look at different types of relations, and then we'll also discuss the matrix and the directed graph representation of these relations. So, what is a Cartesian product? In the previous video where we covered sets, we spent quite a bit of time towards the end on elaborating about the Cartesian products, but what is important about the Cartesian product is that you look at pairs here now. So number pairs or letter pairs or a mixture of numbers and letter pairs. What's important is in the Cartesian product that the first term of these pairs come from the first set and the second of these pairs comes from the second set. So these are all so-called ordered pairs. The most common example that you have become familiar with in your previous mathematical studies is the coordinate system or the Descartes system, where you look at the coordinate of a point, you always call the x coordinate first and the y coordinate second. So, what is a relation? Now, if A and B are sets, then a binary relation for which we use the symbol capital R, from A to B, assigns to each ordered pairs AB in A cross B one and only one of the following statements. A is related to B, for which we're going to use the symbols ARB, or A is not related to B, which we will use the symbol for AR crossed out B. That looks quite a mouthful and a rather complicated definition, but what are we actually talking about in here? So basically, when I'm talking about a relation, I'm talking about a subset of the Cartesian product of A and B. Basically, some ordered pairs from AB will belong to the relation and some will not. But I will be able to definitely tell you about one ordered pair, whether it's belong or not to the relation. So let's look at some examples. Let's look at set A, which consists of 1, 2, 3, and 4. And let's look at set B, which consists of A, B, and C. And now you are asked to find two possible relations from A to B. All you need to give me now, and I'm going to use R1 for the first relation, pairs where the first belongs to A and the second belongs to B, and I can use any combinations. If I wanted to use, I can use all of them. If I wanted to use, I can use just a few. So for example, I can use 1A, 2B, then 1C, and let's say 4B. That can be my relation. I could add more of these combinations to it, or I can take away some and then I can give another one. So let's look at R2. Let's say it 1A, 1B, 1C, then say 2A, then 3C, and use 4B. Now I can say that the two relations are different, but they also have got common terms in them, but they are two definitely different relations. Now the importance here is that all of these terms in the relations have to belong to the Cartesian product of A and B, and when I look at a relation about the Cartesian product, I can look at, okay, 1A belongs to the relation, but 1B doesn't, because 1B is not in R1. Now, what other elements of the Cartesian product are not in R1? Well, none of the three elements. So 3a, 3b, 3c are not there. Also 2a and 2c is missing, and we also missing 4a and 4c. In this relation we miss less terms, but we still miss 2b, 2c, 3a, 3b, and we miss 4a and 4c. So a relation is always a subset of the Cartesian product. So we use two different ways of representing these relations. One of them is the directed graph. So let's look at an example for a directed graph representation for a relation. So I've got the set A, 1, 2, 3, 4, and I've got the set B, which is 1, 2, 3. So give the directed graph of the following relation from A to B. So A is 1, 2, 3, 4, and B is 1, 2, 3. So 1, 1, so from 1 go to 1. Then I have got 1, 3, so from 1 I'm going to 3. Then I've got 2, 1, so from 2 I'm going to 1, and then I've got 2, 2. Then I've got 3, 1, 3, 2. Then I've got 4, 1, and 4, 2. 4, 1, and 4, 2. Okay, so this is a directed graph when I apply it to two different sets. So A and B are separate sets. A different way of representing these relations is the matrix form. So again, let's have two different sets. A being A, B, C, D, and B being A, B, C. So how am I going to show you the matrix representation of this relation? So I have got the elements from A here, A, B, C, D. And I'm going to have the elements from B at the top. A, B, C. And this is my R4 relation. Now, AA is in my relation because it belongs to the relation set, so I'm going to put a true here. And again, remember A, this is on the vertical and B is on the horizontal. So AA is there, AB is there, and AC is there. BA is there, so that's a true again. BC is there, CA is also there. DA is there, DB is there, and DC is there. And the rest that's missing, I'm just going to fill in with false. It's a little bit like your truth table, but now you obviously have got a lot more rows and columns. And again, what I can see from here is that BB, CB, and CC are not part of my relation. They don't belong to my relation. So this is the basic of the matrix representation. That's how it looks like. And again, in this matrix representation, the truth tells you that the ordered pair belongs to the relation. So in this specific case, the BA belongs to the relation, but BB doesn't because it has got a false in that cell. Now, one reason why relation might prove difficult to some people is that, again, you introduced a lot of new concepts here. So you have to learn, and I cannot stress enough that you have to know these definitions. What is a reflexive relation? What is an irreflexive relation? What does it mean for a relation to be symmetric, antisymmetric, and transitive? Every single one of these definitions you have to know, and you also have to understand. So let's elaborate a little bit on what is reflexive means for a relation. So reflexive means, by the definition, R is reflexive if X are X for all X element A. So for every relation that is defined on the same set A, so again, now we're not talking about two different sets that we're combining together, we're combining the same set into Cartesian product, into pairs, and for every term in that set, if the same containing pairs like AA, 1, 1, 2, 2, depending on if you're using numbers or letters, if every single one of them belong to the relation, then this relation is reflexive. Now the irreflexive is the opposite of reflexive. So if there are no elements of A for which X relate to X, so all of the same pairs like AA, BB, CC, none of them belong to the relation. Well, symmetric is if for all of those element pairs that belong to A, X is related to Y, then Y is also related to X. So for example, if I've got a relation where 1, 2 belongs to the relation, it will be symmetric if 2, 1 also belong to the relation. Well, antisymmetric is slightly different because it means that for all those pairs where X related to Y at the same time as Y related to X, also only true for those elements where X and Y are the same. So this is slightly different. And the transitive, you can think about this as a follow-on relation. Probably the easiest example for the transitive would be the less than sign. So if 1 less than 2 and 2 less than 3, then 1 has to be less than 3. So that's probably the easiest to kind of remember what transitivity means. So basically, if X relate to Y and Y also relate to Z, then X have to be related to Z for the relation to be transitive. And then there is a very special relation which we call the equivalence relation, and for a relation to be equivalence, it simultaneously have to be reflexive, symmetric and transitive. So again, you need to know the individual meanings of the reflexive, symmetric and transitive, and when all of them is true for a relation, then that relation is called an equivalence relation. So let's look at an example. So I've got a set A which consists of 1, 2 and 3, and I define the relation R on this set as to be 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 3, 1, 3, 2 and 3, 3. And now I need to determine whether R is reflexive, symmetric, transitive and or equivalence relation. So let's see what I can say about this relation. Now the easiest way to decide whether something is reflexive, irreflexive, symmetric, transitive is to do the matrix representation. Now this R is defined on A, so the matrix representation will be 1, 2, 3, 1, 2, 3. Okay, so here's the matrix representation. Now I have to put in the trues and falses according to what belongs to my relation and what doesn't. So 1, 1 belongs to there, so I put a 2 in here. 1, 2 and 1, 3 also belongs. 2, 1 is there, 2, 2 is there, 3, 1 is there, 3, 2 is there, and 3, 3 is there. So I'm only missing this. Now, for something to be reflexive, what was the definition? Reflexive was that for every term in A, the same pairs belong to the relation. What I mean by that? So I've got terms 1, 2 and 3 in A, so my relation will be reflexive if 1, 1, 2, 2, 3, 3, every single one of them belong to my relation. And they do, because 1, 1's here, 2, 2's here, and 3, 3 is here. The easiest and quickest way to see it is whether or not your diagonal contains true all the way down to the bottom. So true, true, true. That means 1, 1, 2, 2, 3, 3. All of the same pairs belong to the relation, so it is reflexive. Now I need to double check whether if it's symmetric. So let me give you an example what I mean by symmetric for this specific relation. So I've got a pair here, 1, 2. That belongs to my relation. It will be symmetric if 2, 1 also belongs to the relation, and it does. So next one, 1, 3. Does 3, 1 belongs to? Yes, so that's good. But now look at, I've got 3, 2 here, but the symmetric pair 2, 3 is not in here, so it's not a symmetric relation. So it was reflexive, but it's not symmetric. Now, from the matrix, you can also say this is basically you look at the upper triangle, the triangle above the diagonal, and the lower triangle, the triangle below the diagonal. If they are mirror images of each other, then you got a symmetric relation. If they're not, then you don't have a symmetric relation. So basically this one is not a symmetric relation because this is true here, but that is false here. If both of them would be false or both of them would be true, then we would have a symmetric relation. Now, this is not symmetric, which means it cannot be an equivalence relation because it has to be reflexive, symmetric, and transitive. But let's have a look and see if this is transitive or not. Now, the transitivity is the most difficult one to test because there is no trick for looking it up from the matrix. So what you need to go through is see, okay, 1, 1 is there, 1, 2 is there, 1, 2 is also there. So for these elements, the transitivity holds. But you have to go through for every single one of them and see if you can come up with a counterexample. If there is one term that is not there, it's not going to be transitive. But you don't know until you went through every single one of them. So 1, 1, 1, 3, that again gives me the 1, 3 pair. So what I'm looking at here, this is 1, 1 and 1, 3. So the last element and the first element have to be the same, and then I need to look at if the remaining terms give me a new element and if that belongs to the pairs or not. So 1 is the common element here, and if I take this 1 away from here and combine the two elements together, that would give me the 1, 3, which is exactly the same as this one. So that is actually part of the relation. Then I can look at 1, 2 and 2, 1. So those are again, this is the common element. And then if I delete this element, 1, 1 is belong to my relation. So far it's transitive. 2, 2, 2, 1, that's again two terms. And again, this is the second and that's the first term. And I end up with 2, 1 again, so that's transitive. If I see 1, 3, 3, 1, that gives me 1, 1 back, that's still transitive. 1, 3, 3, 2, 1, 2 is there, so that still holds the transitivity. 3, 1, 1, 3, that gives me 3, 3 back. Have I checked everything? 3, 2, 2, 2, that gives me 2, 2 back again. 3, 2, yes, so I can say that this relation is transitive, but because it's not symmetric, it's not an equivalence relation. So again, the tricky bit will be the transitivity because you have to actually go through all of the pairs. Again, the trick here is you pick up terms like 1, 1 and 1, 2. The important here is that the first term's second pair and the second term's first pair have to be the same. And then when you delete those, you end up with a pair of 1, 2, and then you double check if that belongs to the relation or not. So in this case, because this ends up being the same as the second, it is there. But let's look at a slightly different example. So I have got 1, 3 as a pair. Then I can pick up another term which starts with 3. And again, these were the common terms. And if I delete those ones, I've got 1, 1 here that belongs to my relation. So these elements are fulfilling the transitivity criteria, but I have to go through every single one that's possibly in here. Let's look at one more example just so everybody is on the same page. So look at 3, 2, 2, 1. Okay, so the common terms now, 2 and 2. So if I delete them, I end up with 3, 1. And yes, 3, 1 is in there. So that every one of them actually satisfies the transitivity. And I have to go through all the possible combinations. And unfortunately, unless in the case of reflexive and symmetric, I cannot just look at the matrix and say, okay, because the diagonals are all true, it's reflexive. There's no such thing for transitivity. So you have to go through and play around with all these numbers. Now, what I'm going to do, I'm going to give you one more example of these relations, and we're going to look at whether this one is reflexive, symmetric, transitive, or equivalence. And that will be about relations. So, in this next example, I still got the same set of 1, 2, and 3, but now the relation is defined as 1, 1, 1, 2, 2, 1, 2, 2, and 3, 3. So it's a slightly different relation. Again, draw up the matrix. Okay, so here's my matrix. Now 1, 1 belongs there, so I put the true there. 1, 2 is true, 2, 1 is true, 2, 2 is true, and 3, 3 is true. So I'm going to put the false symbol into the rest of them. So again, I need to check whether if it's reflexive, symmetric, transitive, and if it's all three of them, then I can say that this is an equivalence relation. So reflexive, well, the diagonal, true, true, true. So every single term that's in A, its corresponding pairs of 1, 1, 2, 2, 3, 3 are in the relation. So yes, it is reflexive. Symmetric. If I look at the upper triangle and the lower triangle, they are mirror images of each other. True is here, true is there, false is here, false is there, false is here, false is there. So yes, this is symmetric. Another thing, 1, 2 is there, so 2, 1 is there, and the rest of them aren't. But for the symmetric to be true, it doesn't mean that every single pair have to be in there. It's just saying that if 1, 2 is there, then 2, 1 has to be there as well. But all the rest of them are the same terms. So luckily, it's just one pair that we needed to double check. Now comes the transitivity. Now this is the tricky bit. This is we have to go through the pairs. So I'm going to draw out a few of them like I've did in the same in the previous page. So 1, 1, 1, 2. If I delete the middle ones, I end up with 1, 2, which is obviously in there. And there is no other terms that starts with 1. So I can go into 2, 1. And 2, 1, the only term, there are two terms that starts with 1. So I can look at the 1, 1. If I delete the middle terms, I end up with 2, 1, which is in the relation. And 2, 1, the other term that starts with 1 is 1, 2, and if I delete the middle ones, I end up with 2, 2, and 2, 2 is in my relation, so the transitivity still far holds. Then I pick up 2, 2. There is only one term that starts with a 2. That is 2, 1. And if I delete the middle ones, I end up with 2, 1. That is in there. So far, so good. And what's better is that there are no other terms that start with a 3 other than the 3, 3. So I don't really have to double check the transitivity for any other terms, which means that this relation, yes, it is transitive. So it's also an equivalence relation. Now, I hope I helped you to understand relations a little bit better, but feel free to get in touch and email me if you think that I could clarify things a little bit better, or if you would like to book a tutorial.